Okay, over to Stuart, who doesn't normally look so posh. He's been in the
Not
house
usually so
long.
tidy. Yeah.
Over to, so Stuart's going to talk a little bit.
Have you got your? I'm off. Yeah. You need to turn your sound on. As well. Not your. Hang on.
The boys are both at the Royal Society because they're both.
Okay, can you hear me okay?
I can hear you now. So there's Stuart's information. If you can keep it relatively
can you hear me
brief,
okay?
Stuart, that'd be great. Yes, we can.
Yeah, sorry, we were getting some reverb. Okay, I'll just share my slides. Can you see that okay? Yes. Yeah. Okay. So, Shelley, can you see that? Yeah.
I can. Perfect. Thank you. So you've got about sort of a little bit more like 10 minutes if you can keep it to that. That'd be great.
Yeah. I'll go quickly then. Okay. Well, I think a lot of these concepts have already been introduced. So a lot of what I'm going to talk about is some general considerations for the when manipulations of the lighting in the care home environment, and I think generally manipulations for human studies generally. So we know about the different types of image forming and non-image forming responses to light, so I won't go into that in detail. And of course we have these melanopsin photosensitive retinal ganglion cells, which are critically important in these responses. And a key point that actually has been raised already is the fact that photopic lux does not accurately reflect these responses, and this led to the development of this concept of melanopic lux, or melanopic equivalent daylight illuminance, which is now being widely used to actually try and capture the different spectral sensitivity of these non-visual responses to light. And actually using the same sort of system, you can actually calculate for any light source, you can calculate the activity of any retinal photoreceptor, rods or red, green or blue cones. And this is what you refer to as alpha-opic lux, where alpha is the type of photoreceptor you're referring to. So you can apply this to basically all the photoreceptors in the human retina to describe these different responses to light. And working with Manuel Spitzchen a few years ago now, and Forrest Webler, we were discussing this in terms of actually the light environment is actually a lot more complex than we sort of often presume. If you consider a scene like this, you have different areas which have got natural light, you've got artificial light sources, you've got reflected surfaces. So actually, the light environment is more complex than we often give it credit for. And so different areas of visual space will actually have different spectral, a different spectral makeup. And these different parts of the visual scene will fall onto different photoreceptors on the retina, the red, green and blue cones, the melanopsin and the rods. And so actually this, it potentially creates a lot more complexity than we often consider. And of course, much of the laboratory data we have on this is using full field illumination, where the whole visual field is actually exposed, as opposed to the natural light environment under real world conditions, where our eye movements, head movements will actually mean that the light falling across our retina is constantly changing, which may mean that we actually have different contribution of visual photoreceptors too. And whilst this does seem, now there are small spectrophotometer devices whereby we can measure the wavelength of light, shown here at the top, across a whole day, and look at how the spectrum that any one person is exposed to varies. And from that, we can calculate the photopic lux, we can calculate melanopic lux and see how those vary, and even express them as ratios. But one thing we find when you start looking at this is there are many regularities. So people typically spend their time in the same environment, and in a care home environment, as Shada beautifully showed before, actually you really need to consider areas where people sleep and areas where people don't sleep, and that is probably a very sensible way of capturing that sort of statistical regularity in the environment. But a lot of these changes are really dominated by changes in intensity rather than necessarily large changes in the spectral composition. And based upon a recent expert working group, Tim Brown reanalyzed data from human melatonin suppression, circadian phase shifting, and subjective alertness. And this is largely data from the Harvard lab and from Basel, from Christian Kjokken's group. And you can express these as like a drug dose response curve, where you have a drug dose of, well, where you treat light as a drug, whereby you have the dose on a log scale of melanopic EDI here, and you see basically you go from having no effect, a biological effect, to an increasing effect up to a point of saturation. And based upon this, you can actually try and provide some sort of indication of what the the levels of light, for example, daytime indoors should be around sort of 250 melanopic lux. So you're up here on this curve, and if pre-sleep, you want to be below sort of 10 melanopic lux, and on a night when you're sleeping, below 1 melanopic lux. And this is based upon trying to actually minimize known biological effects. So these responses occur over several log units. And similarly, I mean, just this going back to old data from Bud Brainard on melatonin, an action spectrum for melatonin suppression, we can actually see it is possible to get, you see these responses to different wavelengths of light. They all show these dose response curve characteristics, and even with where the response is more sensitive, this curve is pushed in this direction with blue light, and where it's less sensitive, it's pushed in this direction towards the right. And as a result, you can actually still get responses with red light, you just need more of it. And so all of these responses we really ought to be considering as these dose response curve kind of responses. Thinking of this, for example, just a quick illustration of the effects of warm versus cool white light. We can calculate the level of alpha-opic lux for each of these pigments. 100 lux, for example, of warm versus cool white light would give us nearly 100 lux of melanopic EDI for the cool white light, but only about 46 for the warm white. So this actually is about a twofold reduction in melanopsin activation. But actually, if you consider that on this scale of the dose response curve scale, we're talking about a difference of that. So actually, this is probably within the error, and to be able to measure a difference like that, we would need a very large sample size to be able to get that resolution, to be able to measure that in practice. So again, it's a 75% versus a 60% response. And so actually changing intensity is also quite important when you're changing correlated color temperatures. Similarly, blue blocking will actually, so this is daylight, typically blue blocking, people cut out below 500 nanometers. It still leaves this whole area of the melanopsin sensitivity curve actually where the is still capable of detecting light and responding to light. And again, on a log dose response curve or a radiance response curve scale, that's a difference of about there to there. So it's not perhaps surprising that, in many studies using blue blocking glasses, these studies show no effect. So about, in patients with individuals with normal sleep, around half of studies show some effect, half of studies show no effect. But one of the key points is you need to know the incident light levels, because if your light levels are up here, reducing those by a small amount won't have any effect. If they're down here, then you may be having no effect anyway. So you need to know what that actual incident light level is as well. Another point on the transmission of blue blocking glasses and blue blocking filters is people often don't report the transmission. Sometimes people typically using below 500 nanometers, some people are actually using at 550 nanometers. That may be expected to have a much greater effect, because actually you're then starting to get up to a 16-fold over a log unit difference in actual light intensity. So, and also one other point just to make in this whole field from recent data, of which the Harvard lab again have been critically involved, along with groups from Monash, is there's a big variability in individuals' responses to light. We don't yet know why, whether these are differences in things like the melanopsin protein, but actually there are big differences between individuals, and that is often not taken into account when studying larger populations. And again, the amount of light required to get a 50% response can vary about 50-fold from 6 lux up to 350 lux. The time of day of the light exposure also is critically important. Light on an exposure on an early night will result in a phase delay. Light exposure later in the night will lead to a phase advance. And our modern light environment, work from Ken Wright has shown that actually the modern light environment primarily differs from the natural light environment in two ways. We're exposed to less light during the day in the modern artificial light environment, and we're also exposed to this dim light on an evening. And this leads to changes in melatonin changes in sleep episodes as well. And of course, that's because our exposure to light is typically into the evening. This shows the human phase response curve to light from studies at Harvard, showing that actually, that the timing of light exposure is also critical and should be taken into account in these kind of studies. And finally, just want to really under some of the points related, of course, critically to aging and the aging population. The non-visual effects of light in aging population can be affected by a huge range of different factors. So lens transmission, shown in this graph here, varies enormously across age from children all the way up to elderly individuals. There's a reduction in the total amount of light transmitted by the lens, and also particularly cut off at shorter wavelengths. There are many other factors as well. So the pupil size is typically smaller with age. There can be changes in chronotype, actually less sleep consolidation, reduced activity levels, and there can also be specific illnesses and medication effects, which may all modify the responses to light interventions. So in terms of going forward, I think just want to emphasize that this visual and non-visual photobiology is a complex and fast-moving field, and many simple lighting solutions that are often recommended may actually produce very small effects unless intensity is also taken into account. Changes in intensity are typically, I say, often greater than the changes in wavelength. And actually taking a quote really from Steve Lockley at Harvard, who Shadab has worked closely with over the years, that you could basically consider that light is a drug, and its effective use depends upon the right dose at the right time in the right context. And I think really as well, we need a better dialogue between basic scientists and lighting engineers to translate these findings really into practice. So with that, I just want to thank my lab and collaborators, thank you for your attention.